The premise of this presentation is that we really can't tell how old a universe is. Again, I will present the standard accepted version of how we determine the universe age, and then I explain the flaws in this reasoning. As usual, you can select the topic that interests you or follow the entire presentation. To determine the universe age, we need to assume that the Big Bang did happen. Time is not eternal, but was created during or after the Big Bang, and time has always evolved at the current rate throughout the entire universe, disregarding the effect of gravity and temperature. If any of these postulates are incorrect, it becomes impossible to determine the universe age. The picture in this slide is a visualization of the Big Bang as seen from outside the universe, which is an impossibility since we don't know what's outside our universe or what can be seen from outside the universe. As for the Big Bang itself, it was not an explosion in space, but an explosion of space. It created space and propelled space and energy with some undeterminable acceleration away from the point of origin. Or maybe energies were propelled space. Either way, scientists call this the inflation era. The accelerated inflation era diluted or thinned out the fabric of space and energy, a problem magnified when these entities condensed into matter. This condensation ended when the amount of available energy was insufficient to create additional matter. By then, the removal of energy from the universe stopped the accelerated inflation and set the speed of universal expansion at the speed of light. By the way, to me the fabric of space is a substance. So while all of this is happening, when did time begin? The question now becomes, how do we compute the universe age? In other words, how much time has elapsed since time first appeared? Which is not the same question as when did the Big Bang happen? The answer to this question, we rely on three methods: the temperature of the coolest stars, the cosmic distance ladder model, and the Lambda-CDM model. The universe must be older than the oldest stars. And we know the lifespan of stars since small stars burn their fuel slowly, therefore they last a long time, while larger stars burn their fuel very fast and are short-lived. In the universe, we see globular clusters composed of small stars, which means the universe is approximately 11 to 18 billion years old. Not a very accurate figure, but a ballpark figure. Another way to measure age is by measuring the Hubble constant. That's a number that tells us how fast the universe is expanding and in which direction. We can get this number by measuring galactic motion and applying two basic physics concepts to this motion. The first one is the inverse square law, and the second one is the Doppler effect, the Doppler shift. The inverse square law states that the intensity of radiation is inversely proportional to the square of the distance. What it means is that the closer you are to a source of energy, the more intense the energy appears. So if you know the brightness of an object and you measure its apparent brightness, you can compute how far it is, since darker means further. Astronomers found a type of supernovae called 1A that always reach the same brightness. By measuring their apparent brightness and knowing the real brightness, we can tell how far these supernovae are. The other concept is the Doppler shift, the Doppler effect. This is just a change in waves noticed whenever there is relative motion between source and observer. What it means is that whenever a wave source moves toward an observer, the waves get compressed, making the frequency appear higher. And when a wave source moves away from an observer, the waves get stretched, making them appear lower. By measuring the supernovae wavelength or frequency change, we can compute the source velocity and, more importantly, its direction. These two concepts tell us how far, how fast, and in what directions galaxies are moving. Closer galaxies are moving away from us slower than galaxies that are further out. And in terms of distance, each galaxy away from us seems to form the rung of a ladder in terms of distance. That's why we believe the universe is expanding and how fast. Once this expansion was discovered and measured, the next logical step was to run time backwards. Since there was nothing to prevent the universe from shrinking indefinitely, scientists decreed that the universe formed 13.77 billion years ago as an extremely hot and dense dot. This method gave us a more accurate age compared to the age as determined by the stellar temperature. It is believed that a quark gluon electron plasma was created during the Big Bang. Almost instantly, quarks formed protons and neutrons, and soon after, some of these protons and neutrons formed the nucleus of deuterium, tritium, and helium. But the universe was in a very high energy state, and that energy prevented electrons from joining these nuclei into atoms. Simultaneously, energy was prevented from escaping the plasma. Energy was constantly bouncing back and forth between the plasma particles. After a brief period of inflation and 380,000 years of expansion, the universe cooled to 3,000 degrees, cool enough for electrons to be trapped by the nuclei and form hydrogen atoms and helium atoms. This is called the recombination era. This recombining made the universe transparent, which allowed light energy to escape from matter and expand outwards. So in this sequence of events, the question we have to ask again is, when did time start? The light energy from that time is still bouncing around the universe, but universal expansion has lengthened the light's wavelength into the microwave region of the spectrum to a temperature of 2.7 degrees Kelvin. We call this the cosmic microwave background radiation since it's everywhere. So by measuring how much a light wavelength has been stretched, accounting for small differences in the temperature of the light, and including dark matter, dark energy, and gravity's effect on the equation, scientists created several models. One of these models, called the Lambda-CDM model, matched the result from the latter model with a small difference. It predicted the universe to be 13.8 billion years old. Now, there are flaws with these models. The cosmic distance ladder measures galactic motion in our universe, and we assume this galactic motion is caused by universal expansion, namely that the universe is expanding at the same speed as the galaxies are moving. But universal expansion is the expansion of space, not matter. And universal expansion cannot move matter. That's Newton's first law. I have a video on inertia explaining this. Since we don't know when time first appeared, we don't really know when atoms were created or when energy began propelling them. We assume it happened 380,000 years after the Big Bang during the recombination era. At this age, energy propelled matter at a speed that could not exceed the speed of light. This makes a 13.77 billion years age speculative. The information we're basing our beliefs on are anchored to the speed of light, but we know temperature and gravity affect light speed. We can slow down light to a stop in a Bose-Einstein condensate, and the universe can stop time at the event horizon. The problem is that we measure light speed on the Earth at a certain temperature and in Earth's gravitational field. Any difference in the value of the speed of light will invalidate our results, especially when we are dealing with distances in the billions of light years and temperatures since the beginning of the universe. The Lambda-CDM model has its own problems. We believe light bounced between plasma particles, therefore it could not escape from the plasma. In reality, there was no space for light to escape into. The entire universe was the plasma. So let's say after 380,000 years, and we don't know what that number means since we don't have a starting point yet, the plasma cooled enough for atoms to form. Light still couldn't escape, since for a moment there was no space outside the plasma atom's universe for light to escape into. Afterwards, space expanded at light speed, but matter had to lag behind at less than the speed of light. Although the cosmic distance ladder value of 13.77 billion years old was arrived experimentally by measuring galactic expansion, not space expansion, it became the gold standard, and all of the values had to approximate that value to be scientifically acceptable. Scientists created and discarded various models until they came across the model that approximated the value of the cosmic distance ladder method. The Lambda-CDM model value of 13.8 billion years was the closest, therefore that became the other acceptable model, even though it included dark matter and dark energy, two variables that are still debated. With the cosmic distance ladder, the Lambda-CDM, and the speed of light suspect, how can we date the universe? The only physical, definite known data is today's universal temperature of about 2.7 degrees Kelvin. If the universe is expanding at the speed of light and we knew its radius, we could easily compute when it formed, but a possible uncertainty in the speed of light makes the determination of the universe's radius suspect. If we assume the universe is round, we could determine its volume using basic geometry. Volume is equal to 4/3 pi r cube. But we're not sure of the radius since the accepted value of the universe is 13 billion light years, a questionable value due to the inclusion of dark matter and dark energy. Assuming a constant light speed, a possible solution could be found if we could determine the temperature and volume of the universe at some past point. If we had that, we could easily determine the universe volume right now. Could we use the volume and temperature at the recombination era? In chemistry, there's a law called Charles' law that relates the temperature and volume of a gas under constant pressure. Assuming space to behave as an ideal gas, a gas that's point-like, has no volume, and we believe there's no outside pressure on space, if we plug in the temperature in today's value and the volume and temperature at the recombination era into Charles' law, we could compute our universe current volume. But in this instance, Charles' law fails. The question now becomes, why does Charles' law fail? Does it not apply to the universe? Or is the current value of the universe temperature wrong? Or are the value assumed from the recombination era wrong? Can anyone out there suggest any other reason for this failure? Until then, the universe age remains indeterminate. So in conclusion, the cosmic distance ladder method to determine the universal expansion and age fails since it only measures galactic expansion, not space expansion. And the Lambda-CDM method fails since it relies on the cosmic distance ladder method as a benchmark and requires the presence of dark matter and dark energy. The only definite value to determine the universe age is the current universe temperature of about 2.7 degrees Kelvin.